Welcome to a technical deep dive on large language models, LLMs, the engines behind today's generative AI. At their core, LLMs are probabilistic sequence models trained to predict the next token given a context. That simple objective yields powerful emergent abilities: reasoning, summarization, coding, translation, and tool use. In this episode, we'll map the terrain, the transformer architecture, the attention mechanism, training objectives, decoding, types of LLMs, efficiency tricks, safety and evaluation, and where this tech is headed. Keep in mind a mental pipeline. Text becomes tokens, passes through stacked transformer blocks, and returns probabilities over the vocabulary, one step at a time. By the end, you'll understand not just what attention is, but how modern LLMs are built, trained, and deployed. The transformer is today's dominant LLM architecture. In a decoder-only model, input tokens are embedded, then passed through many identical blocks. Each block has two major sublayers: self-attention and a position-wise feed-forward MLP, wrapped with residual connections and layer normalization. Stacking dozens of these blocks increases the model's capacity to represent complex dependencies. Finally, a linear LM head maps the top layer hidden states to vocabulary logits or next token probabilities. Decoder-only architectures are optimized for autoregressive generation, while encoder-decoder models shine in sequence-to-sequence tasks like translation. Now, let's open the black box of attention. Self-attention lets every token weigh other tokens in its context. We first linearly project hidden states into queries Q, keys K, and values V. Then we compute scaled dot products, QK transpose, divide by the square root of the key dimension, apply softmax to get attention weights, and finally form a weighted sum of the values V. Intuitively, a token asks, which other positions are relevant to me, and gathers information accordingly. In causal language modeling, a triangular mask zeroes out future positions, so the model only attends to the past. This mechanism replaces recurrence with direct, parallelizable context mixing. Multi-head attention runs several attention modules in parallel, each with its own Q, K, and V projections. Different heads can specialize, syntax, coreference, or long-range cues, and their outputs are concatenated and projected back into the model dimension. Because the transformer has no inherent notion of order, we inject positional information. Options include sinusoidal or learned embeddings and rotary position encodings that rotate queries and keys in a way that preserves relative distances. Together, multiple heads plus position allow the model to relate words across both short and long spans. Most LLMs are pre-trained with causal language modeling, predicting the next token from left to right. Encoder-Decoder models often use masked language modeling as part of sequence-to-sequence training. After pre-training, supervised fine-tuning uses curated instruction-response pairs to steer behavior. Finally, preference optimization methods, like reinforcement learning from human feedback or direct preference optimization, encourage outputs humans prefer. This multi-stage process converts a general predictor into a helpful assistant, while attempting to reduce unsafe or low-quality completions. LLMs operate on tokens, subword units produced by algorithms like byte pair encoding or unigram. Tokenization balances vocabulary size, compression, and the ability to represent rare words or code. Each token maps to an embedding, a dense vector that captures distributional meaning. Stacking blocks transforms these vectors into contextual representations. Practical note: context length matters. Longer contexts increase memory and compute quadratically for attention, unless specialized optimizations are used. Choosing the right tokenizer and context size directly impacts quality, latency, and cost. During inference, we feed tokens through the model to get logits, convert them to probabilities, select the next token, append it, and repeat. Decoding strategies shape style and quality. Greedy is deterministic but dull. Beam search explores multiple paths: temperature, top K, and nucleus. Sampling add controlled diversity. Efficiency hinges on a key value cache that stores past attention states, so each new token reuses prior computation. Latency is affected by model size, context length, batching, and hardware throughput. LLMs come in several flavors. Decoder-only models dominate chat and code generation, thanks to efficient autoregression. Encoder-Decoder models remain strong for translation and summarization. Encoder-only models, like BERT style, excel at understanding and retrieval tasks. Mixture of experts scales capacity by routing tokens to specialized expert MLPS, improving parameter efficiency. Multimodal LLMs connect text with images, audio, or tools, enabling richer perception and grounding. On top of these bases, instruction tuning turns a raw model into a conversational assistant. Empirically, performance improves predictably with more data, model size, and compute, subject to diminishing returns and balance among the three. Training giant models requires parallelism. Data parallel replicates the model across devices. Tensor parallel splits matrices, and pipeline parallel divides layers. At inference, custom kernels reduce memory traffic for attention. Quantization shrinks weights to 8 or 4 bits, and distillation transfers knowledge to smaller students. Techniques like speculative decoding can reduce latency by proposing tokens and verifying them quickly. Responsible deployment demands safety and rigorous evaluation. Safety work includes minimizing harmful or biased outputs and protecting private data. Evaluation blends automated benchmarks with human review and regression tests to track improvements over time. Prompting practices matter. Use clear system instructions, relevant examples, and constraints. Guardrails, like content filters and restricted tool access, help prevent misuse while preserving utility. Let's consolidate the pieces into an end-to-end mental model. Start with tokenization and embeddings. Stack transformer blocks to build contextual representations. Project to logits. Then decode tokens to form text. Throughout, pay attention to the trade-offs. Longer contexts and larger models improve quality, but increase latency and cost. Decoding parameters like temperature and top P tune creativity, while safety and evaluation keep the system reliable. This mental model helps you reason about failures, performance, and how to tweak a deployment. The frontier extends beyond standalone models. Retrieval-augmented generation grounds outputs in external knowledge. Tool use and function calling let models delegate tasks to calculators, search, or code execution. Agentic systems chain decisions across steps: planning, acting, observing, and refining goals. Meanwhile, efficient, quantized models enable private, low-latency on-device inference. Together, these directions point to LLMs that are more factual, capable, and accessible. And that wraps up our deep dive into LLMs, attention, architecture, and everything in between. If this helped you think more clearly about transformers, please give the video a like, subscribe to the channel, and tap the bell so you won't miss upcoming breakdowns on RAG, tools, and on-device AI. Got questions or requests for the next topic? Drop them in the comments. I read them all. Thank you for watching, and I'll see you in the next one.